Hello, my sweet friends. Welcome back to this, to me, to, yes, neural networks. Woo! So, this is the second time I'm recording this. I had like these ambitions of having like a live reaction as I'm learning neural networks, but I forgot to hit record. I hate it when I do that. So, this is not my live reaction, but that's okay. We're going to learn anyway. So last week I explained neural networks, and this week I gave it a go. I decided to try neural networks for the first time, and I'm going to bring you along with me. So let's step into R. Woo! Here we are. Wow. You look so beautiful, R screen, so I'm going to require FlexPlot, because I'll probably end up using it. Tidyverse, I often end up using that. Now, we've got a couple of packages. Reticulate is a interface between R and Python. And I think what it does is it allows R code, it basically translates R code into Python. And TensorFlow is very similar, except it specifically interacts with TensorFlow within Python. And then Keras is, I don't even know if I'm saying that right. It's putting it all together. And by the way, normally I do require, but I got an error earlier because I had require, I guess. I had an error that was fixed by using library. I don't know why. But I've always used those interchangeably, but apparently not. Anyway, so I'm going to be working with the health and depression data set. And this is just some code. I'm taking away the total scores for IAT, which is internet addiction, HPLP, which is health total scores. And I'm taking those away because I have the subscales and the total scale. And the total scale is just a composite of the subscales. So it doesn't make sense to include both of them and just give myself more data. I'm getting rid of the total scores and just keeping the individual subscales. And then I am scaling everything, or basically giving it a mean of 0 and standard deviation 1. And the reason I'm doing that is because apparently neural networks perform better when they're scaled. All right, and then one thing about neural networks, like I really like formula notation, like with LM, it's y tilde x1 plus x2, data equals d. I really like that notation, but for some reason, Keras or Python or whoever, they hate that notation. So instead, you got to create matrices. So I'm creating a matrix of the predictors, where I'm getting rid of the depression variable and converting it to a matrix, because you have to have it as a matrix in order to do the computations. Another thing that annoys me as a package developer, I think it shouldn't matter, but apparently it does. And it, by the way, it doesn't have to matter. If you are a package developer, you should not require them to be matrices. If they give you a data frame, add an if statement that says, if it's a data frame, convert it to a matrix. So I don't have to do that as the user. Anyway, that's my opinion on things. All right, now we get into the model. So we are going to specify how the neural network looks. So we are basically giving it an empty model here. And then we are piping or adding to that a layer of neurons. Units equals 8, meaning we're asking it to come up with 8 different neurons. And then the activation is RELU, which stands for rectified linear unit. And I don't know why they call it that fancy name. Basically, it says if the prediction equation is less than 0, make it 0. Otherwise, leave it as is. So apparently that yields some nonlinearity. And then input shape, that's just telling it how many predictor variables we have. And then we got another layer that has 4 neurons instead of 8. And it's using the same activation function. And then finally we get to the last one, which units is 1. In other words, we're trying to just predict the outcome variable. And there's not going to be an activation function because the relationships are primarily linear in this data set, so I don't need the outcome to be predicted non-linearly. And then we get down here and we are compiling the model, which basically sets it up to actually run. It's not actually running it, it's basically specifying the parameters that we need it to run. So loss, we're telling it to compute the loss function for the optimization function using mean squared error. And then it is using an optimizer called optimizer_atom. I don't know the different optimizers they have. But apparently that's a good default one, I guess. And then metrics. Here you can specify additional metrics you want to track when it's computing things. And I asked it to compute mean absolute error. So now the model is set up. And then at this point, I'm going to go ahead and run all that. And it does give me warnings, and I chat GPT'd things and said, is this a problem? And it said it wasn't a problem. I don't trust I don't trust chat GPT. I don't trust chat GPT.
Today, Junior?
So if that is a problem and you know, let me know. All right, now this part of the code, you can see that it's running. So you see a plot on the bottom and a bunch of code on the right, giving you the progress as it goes. And I'll talk about what that means. So we're saying fit the model. We're specifying X, which is what we created earlier. We're specifying the Y, and then epochs. So this requires some explanation. Epoch, really cool word. It sounds like epic, which is a really cool word. I am glad I have that in my vocabulary now. So epochs equals 100. What does that mean? Basically what that means is it's going to run the neural network 100 times. Why 100 times? Well, what it's actually going to do is the first time, after running it with random values, it's going to use the optimization function to find the optimal fit, and then it's going to iterate until it finds the optimal fit. And that constitutes one epoch. And then it's going to do that again. So then when it runs it the second time, it's going to pick up where it left off. So epoch 1 gave it, here are the optimal values for your parameters. And so on epoch 2, it's going to start at that same location and then optimize them again. That confused me a bit because when I think of optimization, I think optimal or the best. So if you've already found the best solution at epoch 1, why are you picking up where you left off and trying to maximize it and trying to find optimum again? That didn't make sense to me. And after a bit of research, I found out why. What's happening, we got some hints down here. We see this batch size equals 4. So what I didn't realize is that it's not actually taking, let's say you got 100 data points. It's not actually performing the neural network on all 100 observations. It's taking 4 at a time for each epoch. So maybe on epoch 1, it's going to sample person 2, person 55, 78, and 91. And then it's going to optimize for just those 4 people. And then now at epoch 2, it's going to randomly sample a different set of people. And it's going to input as the starting function the epoch 1 optimized values. And then it's going to optimize again. And then on epoch 3, it's going to find 4 new people and start where epoch 2 ended. And keep doing that over and over again until we reach 100. But even if your batch size was equal to your sample size, you would still get variability. And the reason why is because what's happening is, there's the hint down there, you've got a training and a validation set. So at each epoch, it is randomly sampling 80% of the data and using that 80% to train the model and to optimize the model, and then evaluating the fit with the remaining 20% of the data. And so at each epoch, it's going to have a different composition of people. So of course, it's not going to find the same solution every single time. In addition to the fact that, like with so many parameters, it's going to be a super bumpy optimization landscape. So all those reasons are why you have multiple epochs, and why optimization at epoch 1 doesn't mean that you found the solution. And so what's happening here on the right in the top screen is it is telling you, it's basically helping you track the progress. So this is 83 out of 100. and then it's reporting the loss function, the mean absolute error, and we'll talk about the other ones down here because this actually conveys basically the same information. So what we have on the x-axis is the different epochs going from 0 to 100, and then the y-axis is either loss for blue or value loss. So what's the difference? Loss is on the training set, value loss is on the validation set. And so not surprisingly, on the training set, it's always going to get better, whereas it may not on the validation set. So in other words, we may have overfit. It looks like we may have overfit just a little bit. So at epoch 9, we found our best value probably. And then as we kept trying to optimize, it started getting a little worse until it kind of leveled out. And so that's loss. And the loss in this case was defined as mean squared error. And here it is in mean absolute error units. And you got the same thing with the training and the validation set. So that's what's happening. Kind of cool. And if you know anything about Bayesian, this looks very familiar. We've got similar ideas in Markov chain Monte Carlos. All right, so that's how things are looking. And then we can do model evaluate, and it will tell you the final solution. So it's got a loss function, a mean squared error of 54.716 with a mean absolute error, or on average, we are off by 5.3 points-ish. And just to give you an idea of what that might look like, so this is the CESD, stands for the Center of Epidemiology Studies in Depression or something like that. Oh, so it's a depression scale. So it ranges from 0 to 60. Let's look at what the standard deviation is. Standard deviation of D, $CESD. So the standard deviation is 8.73. Now it's not normally distributed, but essentially you are within a standard deviation of your error in prediction is usually within a standard deviation, which maybe that's pretty good. I don't know. So now, because I'm a visualization guy, I wrote a function to plot it. Now let me just briefly explain what this is doing. This is a very common plotting strategy that you will see a lot, especially with me. I use it all the time. If you ever use the compare.fits function or the visualize function in FlexPlot, this is happening in the background. So what this is doing is it is creating a brand new data set. Let's say you've got 10 predictors. What it's going to do is for each of those 10 predictors, it's going to create a data set with, let's say, 100 observations. And for those 100 observations, it's going to predict the mean for each of the predictors. Or in other words, it's going to be a matrix with 100 rows, and each of the columns is just going to have that variable's mean. Boring stuff. But then what we do is we take one of those variables. So we'll look later and find out that salience ends up being the most important predictor. Or in other words, it's the most salient predictor. Pun intended, yo. So then what it's going to do is it's going to take that column that has just a mean for every row, and it's going to replace it with a sequence of values, starting from the minimum of salience and going to the maximum of salience in very tiny increments. And so what you have is you have a brand new data set where it has means for everything else except one variable, which is varying across its entire range. And then what you can do is you can feed that to the model and say, hey, based on the model that you fit, what do you predict for this data set? And the cool thing about that is when you do that, then you can see what the model is saying about this variable. So it will show you how the model varies its prediction depending on how salience varies in this case. And I've also got another function here called compute variable or permutation importance. And I don't know if this is the right approach to go. I think I mentioned in my last video, as a statistician, I'm very familiar with thinking about data sets in terms of variables and trying to figure out which variable is the most important variable. But with neural networks, it's not really about variables, it's about representations. So if you're trying to think about generating an image, you might have three variables: X coordinates, Y coordinates, and RGB value, which I guess RGB would be three values. But anyway, you've got all these variables, which that information alone, we can't glean any insightful information from that. But what the neural network is doing is it is generating representations. Like, hey, here's a specific shape that I'm generating, or here's a specific cat that I'm generating. And so neural networks think in terms of representations, but I think in terms of variables. And so I don't even know if this makes sense to compute variable importance, but I think it still does because in this data set, the variables do make sense. So even though the neural network might be coming up with representations that make sense to the algorithm, I think it's okay that I'm thinking about variables and what these variables mean. So I'm going to compute variable importance, and basically all that's doing is it is going through each of the predictor variables, looking at the model, it's computing the fit for the original variables, and then it's going to shuffle that variable. And the basic idea is if you shuffle a score and try to predict something, those shuffled scores should essentially be random. And if there's a very large difference between what the model actually predicted and the shuffled predictions, then that tells you that variable is pretty important. Because shuffling at scores or making them random means your accuracy drops significantly. And so that's something that we do in random forest. And so I said, all right, let's do that in neural networks. And so when we do that and compute variable importance, we find that the most important predictor is salience, followed by self-actualization, then nutrition. So I started looking at what these variables look like. So I use this plot NN function to see what happens. And sure enough, salience being the most important predictor, we see a strong relationship. And what's cool to me, I don't know that it's surprising, because regression could do this, random forest could do this, but it's still at least comforting to know that the fits of the model are passing through the center of the data, as it should. So that's a good validity check there. And it's telling us that as salience goes up, depression goes up. Salience, I think, is like, this is part of the internet addiction subscale, so how salient are internet addiction cues, I guess? I don't know. And then the next one is self-actualization, and if I remember right, that's a pretty big drop. Yeah, so it goes from a variable importance of 3 to 0.66. So let's see what happens there. And yeah, compared to the last plot, that slope is much less steep, but it's still passing through the center of the data, which is great. And so the visuals are matching what the variable importance is telling me, which is informing me what the algorithm is picking up. And so everything looks good so far. That's great. Now, if we look at BMI, which was the least important predictor. Oh, I'm sorry, it's not BMI. Okay, it was on the last iteration that I did that. But let's look at lack of control. And by the way, since this is all random, you may get different results every time. And look at that. It is the least important predictor, and I can see why. That slope is very, very flat. And there doesn't seem to be a very strong relationship between one's perceived lack of control and their self-reported depression. So that's just a quick demonstration and overview of how to fit neural networks in R. And I'm left to wonder, where do we go from here? I'm not entirely sure, but I'm pretty sure I'm not done yet. Because when I discovered random forest, I was working as a biostatistician at the time. And my boss said, hey, I keep hearing about random forest. Can you look into that? And to be honest, I kind of internally rolled my eyes and thought, this is probably some dumb thing that somebody who doesn't know what they're talking about invented. And then I started reading up on random forests, and I was like, wow, this is actually pretty amazing. And I regularly use random forest now. And I'm very glad I did. And I'm very glad I was open-minded enough to explore them. So much so that I eventually wrote a paper that became one of my most cited first author papers that introduced a strategy for using random forests in combination with linear models. And in some ways, it was kind of like a statistician's take on random forests, or how a statistician would view random forest models and use them. And given that that was an influential paper, I started to wonder about neural networks. I wonder if the same thing can happen with neural networks. And I don't know. I think I mentioned in last week's video that the use cases for neural networks tend to be areas that I don't really investigate. Like, I'm not interested in image generation or even image recognition or or anything like that. But I want to remain open-minded just in case there's something here that I might discover that could be a game changer. Because I would love to have another experience like random forests. Like when I learned about random forests, I was like, these are amazing! And it felt too good to be true that there was an algorithm out there that could natively detect interactions, that could natively detect nonlinear effects, and it cross-validated well. Like, what? You can have all those things at the same time? It just seemed too good to be true. And no, it's not too good to be true. That's what random forest models do. They're amazing. And I would like to have another moment like that with neural networks. But I don't know what the use case looks like. So I don't know where I'm going to go from here. I do know there's a couple things that I want to try. One thing is, like the plots that I showed you were just bivariate plots. One variable with another variable. And given that neural networks are really good at detecting very complex interactive relationships, I think it's important to be able to visualize multiple variables at once, which FlexPlot can already do that. I just need to allow the ability to do that for neural networks. And so maybe that will give me some insights. I don't know. I also came across a data set recently. I was actually teaching a live class. And I was talking about how amazing this random forest thing is. And the data set we were using it on, it just didn't do very well. And it was kind of embarrassing. And I wonder if I want to tackle that data set with neural networks. Maybe that'll do better. So that's something else that I'm considering, is finding edge cases where neural networks just blow random forest models out of the water. That would be cool. Or maybe the future looks like using it for something that nobody's ever considered. I don't know. But I do know that I'm not done exploring neural networks. So I hope you will join me as I continue to investigate neural networks. And maybe we'll come up with something like amazing together. That would be cool. And you know what? By the time this video publishes, so it's Monday night right now, I'll probably publish this video on Wednesday or Thursday. That'll be just a few days before my office hours class. And if you don't know what an office hours class is, well, let me tell you. It's basically like statistical consulting, but with multiple people. So I limit it to very small class sizes. I think it's like 5 or 6. And then we just take turns, everybody asking their consulting questions. Sometimes people give me data sets and want me to analyze data and glean information from me analyzing data. And then I spend a little bit of time on each person, and then we go one by one. And so the advantage of that is you get to learn about the questions that you have, but you also get to learn from other people and from their questions. And so it's very unstructured. And sometimes what people decide to do is they want me to teach them, ordinal logistic. And so maybe on week 1, they all agree, let's talk about ordinal logistic. And then I'll do a walkthrough the next time. So very flexible, very open to whatever you guys want to do. So if you are interested, be sure to check out the link in the description. And I've also got a mixed models class coming in September. And then I think I got a visualization class coming in October. So I hope to see you in those live classes. And if the live classes don't work out, then of course you could always do a self-guided class. Anyway, links are all in the description below. So I hope to see you there, my friends. It's been great. Peace out. Hey, let's look at some comments and questions, shall we? Am I worried? No. Maybe I should be. I don't know. I mean, I am a professor, not a data analyst. I don't know. All right, whatever. I don't care. I don't care. I don't care. AI's the future, man. If you don't get on board, you're gonna be left behind. Or maybe the AI ship is sinking slowly itself and all of humanity. Maybe we're all just gonna be out of a job because the robots will take over, like in the Matrix. Maybe none of it matters. Maybe we're all doomed anyway. Wow, that got super nihilistic super fast. I don't even know if we should be doing mediation analysis, like at all. Like it seems to tell us something that we want to know, but I don't think it actually tells us what we want to know. So I've half a mind to tell you never do mediation analysis ever. You ain't never gonna do mediation analysis. What you need to be doing is more theory development. That's what I say. A la Pearl, perhaps, or maybe a bit of, what's his name? Rubin. Donald Rubin, that's his name. That's who I was thinking of. Meh.